Now that we've talked about motion and how things move, and we can describe that mathematically and graphically, we want to get into the why things move. Okay, so we're going to start talking about force. And we all know, and we're probably familiar with the idea that force is a push or pull. Okay, so when you exert a force on an object, you walk up to it and you push on it or you pull on it. Now, it is important to note that force is a vector. Okay, that means when we talk about force, we have to be paying attention to not only how big it is, but also in what direction it's moving. Okay, it is measured in newtons. 1 newton of force is approximately the same as 0.225 pounds of force. Okay, so it takes 1 newton of force to lift and hold a 0.225 or quarter pound about hamburger or so. So a newton is not very much force. Okay. In fact, later we'll define what a newton is and we'll see what it does. Now, whenever a force happens, there's actually two things involved. Okay. These two objects or two bodies push on each other, it turns out, but you can't exert a force on nothing. Okay. So if you're going to push on something, you're what we call an agent because you exert a force, and the object getting pushed is just the object. Okay. So the object gets the force exerted on it, and the agent exerts the force. Now, there's several different ways in which this can happen, and it depends on what kind of force we're talking about. Okay, because there are two major types of forces. There are contact forces, and there are also field forces. Now, contact forces are exactly what they sound like. Okay, two things are in contact. The object and the agent actually have to touch. Okay? And every force that you exert is basically a contact force. If you want to close the door, you walk over to the door and you push on it. If you want to do a chin-up, you grab a bar and you pull on it. Okay, so you pretty much just do contact forces. However, if you've ever jumped, you know you don't jump off the earth. You fall back down. It's because gravity pulls you back down, and gravity is a field force. Okay, it does not require contact. It can act over a distance. You guys have seen this phenomenon if you've played with magnets or static charge, and of course gravity. Right? So gravity holds you down. It's a field force. Charge, um, if you've ever seen like your hair stand up on end, that's a field force from charge. Your hairs get charged with the same charge. They repel each other, even though they're not touching. They push each other apart. And then, of course, there's magnetism, and you guys have all played with magnets. They jump together, they push apart, but they don't have to touch in order to exert forces on each other. Now, we are going to take a look at how we actually draw and keep track of all these forces. And these are what are called a free body diagram. So it's important to note when we draw a free body diagram, we only draw the object, not the agent, okay, but we also label the forces with what's causing them. So even when it's a free body diagram, okay, we still have multiple things in our picture. Now, this first one is called weight, and you guys know what weight is. It's the force due to gravity. So if I had an object that was dropped out of an airplane, okay, I always draw my objects as boxes. Its free body diagram would look like this, okay. This is my object, okay. This little arrow represents the force, and since weight, gravity pulls down, and I label it Fg, force due to gravity, acting on this object. So here's the agent, gravity. Here's the object, the box. Okay, and there's several forces that we're going to use over and over again. So we're going to go ahead and get those out of the way. Okay, so we've got weight, which is the force due to gravity. We've got the normal force, which is a force perpendicular to a surface of contact. Now, perpendicular and normal are actually mathematically equivalent, really. They both mean at a 90-degree angle. So if we took a look at that same box before, instead of thinking about it falling, okay, if it's sitting on a table, okay, the reason it doesn't fall through the table, because yes, gravity is still pulling down, Fg, it's also got the normal force from the table pushing up, and I call that Fn for the normal force. Now, it's perpendicular to the surface it's on. It's not always perpendicular to the object. So if I have a ramp, okay, the ramp actually exerts a force on an object, but it doesn't exert it up. Okay, that's not right. It exerts it perpendicular. It exerts it that way. Okay, it's perpendicular to the surface. Okay? There are a couple other forces here. We have tension. Tension is the pulling force from a rope or a string or a chain or a cable. Okay, tension comes up over and over and over again. We'll use that one quite a bit. Friction, we will actually do a lab on friction, but you guys, for now, it's a force that opposes motion. Now, I do want to take a look at just one more free body diagram so we have a pretty good idea what's going on here. Okay, when you have a free body diagram, the very first thing you want to do is draw the object. It doesn't matter if the object is a helicopter, a person, a tree, it doesn't matter. Objects should be simple. You're not actually drawing a picture of the object, you're drawing a picture of the forces acting on it. Okay, so this is my object, and a lot of times you'll be given a mass. Okay, so a lot of times you'll go ahead and put a mass in here. It'll be a number. Okay, now then you have to label all your forces. So if this thing had the force due to gravity pulling it down, okay, then I would label that Fg. Okay. Now, if it's falling through the air, there might also be a little bit of force from the air pushing up on it. Okay, so I could say force from the air. Okay, and so this little subscript just tells us what's causing the force. But I want you to note something. I did not draw the air right here, force air. We don't do that. Okay, it's bad. Always, always, always start your force vectors, right? These arrows represent vectors on the object and have them push in the direction or point in the direction in which the force acts. Okay, so what I mean is if two people are pushing on a desk trying to get it to move, but they're pushing into each other, so you've got somebody over here and they're like, I want the desk to go this way. And somebody's over here going, but I want the desk to go this way. Okay, and you want to draw a free body diagram of that. You do not draw the arrows pointing this way and this way. Okay? You don't draw arrows into things. You draw arrows on things pointing in the direction of the forces. Okay? So there's that force, there's this force. Now, if this is person 1 and this is person 2, then I could label this F1, can label this F2, because person 1 is pushing to the right, person 2 is pushing to the left. So even now, I still have the agent, the object, the agent, the object. Now we'll take a look how to combine these forces, but you guys already know about vectors, so I bet you have a pretty good idea on that. And there is the case where maybe you've got to consider an object sitting on a surface, okay? And say you're pushing a box this way to the right, so I have the force that you exert, and I'm just going to call it force of the push, okay? And of course, you guys are all familiar, friction is going to be backwards, so we just call this FF, force friction, okay? And technically on this one, if it's resting on the surface, okay, then you still have the force due to gravity, and you still have the normal force perpendicular to the surface. Okay, so this is a free body diagram showing a whole bunch of forces that act on an object, hopefully all the forces. The idea of a free body diagram is to make sure that you have labeled every force that's acting on an object, because that will allow you to determine what's going to happen to the object.